Welcome to this technical deep dive into one of the most significant breakthroughs in modern cryptography and distributed systems. Today, we'll explore how data availability sampling, DAS, fundamentally transforms our ability to scale blockchains while maintaining security and decentralization. If you ever wondered what truly makes modular scaling possible beyond the marketing hype, this presentation will provide the computer science foundations you need. Our agenda today is to unpack the science of scale. We'll start by understanding the fundamental bottleneck in blockchain scaling and why it matters. Then, we'll delve into probabilistic verification, a breakthrough insight that enables us to verify massive chains efficiently. We'll also cover DAS implementation, practical applications, and the computer science implications. Through this presentation, we'll move beyond marketing claims to understand the actual computer science that makes modern blockchain scaling possible. Scaling blockchains requires ensuring that all transaction data is available to all participants, a critical aspect of security. This is particularly important in Layer 2 solutions, where participants must post their transaction data to Layer 1 to ensure security. The core issue, known as the data availability problem, emerges from a fundamental question: how can nodes verify that all transaction data has been published without downloading the entire dataset? Without a solution to this problem, malicious actors could publish only headers or incomplete data, making it impossible for honest participants to reconstruct the state of the entire system. The traditional blockchain architecture faces several challenges. More transaction data means nodes must process and store all this data, requiring increasingly powerful hardware and bandwidth. Higher node requirements lead to increased throughput directly linked to increased hardware requirements. Reduced decentralization occurs because fewer participants can validate and threaten security. This is the fundamental scaling challenge. In traditional blockchain architectures, increased throughput directly leads to increased hardware requirements. The result is a system where efficiency and decentralization must be sacrificed, a seemingly impossible trade-off that limits blockchain adoption. Probabilistic verification and data availability sampling is the key that allows us to verify data without needing to download all of it. This seems counterintuitive, but it's grounded in sound mathematical principles. The key understanding is that if some data is missing, likely by a malicious actor, we can structure the data such that this absence can be detected with high probability by sampling just a small, random portion. We can leverage specific erasure coding techniques to amplify the signal of missing data. With carefully chosen sampling rates, we can achieve near-perfect security guarantees while dramatically reducing verification costs. To understand DAS intuitively, consider a massive 1000 by 1000 Sudoku puzzle. The challenge is verifying the entire puzzle would require checking 1,000,000 cells, computationally intensive and impractical. The strategy is to randomly check a small number of rows and columns. If all checked cells follow Sudoku rules, you can be statistically confident the entire puzzle is correct. Similarly, with blockchain data, if we properly encode the data, using techniques more sophisticated than Sudoku rules, randomly sampling small portions can give us high statistical confidence that all data is available without downloading everything. This intuition forms the foundation of data availability sampling. Data availability sampling uses a specific type of erasure coding, 20 Reed-Solomon encoding, to extend the original data with redundant, parity, information. The original data is arranged in a KXK matrix, which is extended to a 2KX2K matrix by adding parity data. The coding process has a critical property. If even a small portion of the original data is missing, at least 50% of the rows and columns in the extended data will be intact. This amplification effect is what makes sampling effective. The signal of missing data is magnified, making it detectable with minimal sampling. This exponential security scaling is what makes DAS so powerful. The technical implementation of DAS involves several key steps. First, transaction data is organized into a Merkle tree structure, with transactions as leaves and a root hash that summarizes the entire dataset. Then, erasure coding is applied to extend the data matrix using 20 Reed-Solomon codes, creating redundancy that amplifies the detectability of missing data. Commitment to this extended data is published to the root of the Merkle tree, ensuring the integrity of the data. Light nodes randomly select coordinates to sample, request these cells along with Merkle proofs, and verify the proofs against the published root. With sufficient random samples, the probability of accepting a fraudulent block becomes negligible. The sampling process is proposed as follows. The block producer publishes the extended data matrix and its Merkle root. Light nodes select random cell coordinates using a deterministic random algorithm, request the cell data and its Merkle proof from network peers, and verify the Merkle proof against the root. If all sampled cells are available and valid, the node accepts that the data is available with high probability. The beauty of this approach is its asymmetric efficiency. It's computationally expensive for an attacker to hide data in a way that evades detection, but very efficient for honest nodes to verify availability through sampling. The game theory analysis shows why DAS creates such strong security guarantees. Honest block producers who publish all data ensure all requests can be satisfied, all erasure coding checks will pass, and blocks will be accepted by the network. For malicious actors attempting to withhold data, even if 1% of data is withheld, at least 50% of extended matrix rows, columns will be invalid. With just 20 random samples, the probability of withholding data becomes a high-risk, low-reward strategy. The cost of creating a block is wasted if it's rejected. This game theoretic analysis explains why DAS heavily favors honest behavior, making attacks impractical even for well-resourced adversaries. DAS fundamentally transforms the blockchain scaling equation by enabling verification without complete data download. This breaks the traditional trade-off between security and scalability, allowing blockchains to scale without compromising security. Before DAS, blocks were limited by what all nodes can process and store, with hardware requirements growing linearly with throughput. After DAS, blocks can be orders of magnitude larger, with mobile phones participating in verification and decentralization preserved or enhanced. Most importantly, DAS allows block size to increase dramatically without requiring the addition of network participation while enabling massive throughput increases. Without DAS, theoretical scaling is constrained by what the average node can process. Network bandwidth is limited by average node's download capacity, storage requirements mean all nodes must store all data, and verification costs require every node to verify every transaction. These constraints typically limit transactions per second to tens or hundreds. With DAS, these constraints are dramatically reduced. Network bandwidth is limited only by specialized data providers, storage requirements are reduced, and verification costs are lightened as nodes only download small samples. These improvements enable throughput increases of 1000x while maintaining security guarantees and decentralization. Celestia is a blockchain built specifically as a data availability layer using DAS as its core technology. Key technical aspects include modular architecture, focusing exclusively on data availability, separating consensus and execution. Namespaced Merkle trees allow clients to efficiently download only relevant data for their applications. Light node design is optimized for minimal resource usage while ensuring security through DAS. 2D Reed-Solomon encoding provides the mathematical foundation for data availability sampling. Lazy fraud proofs enable nodes to prove that invalid data was published. Celestia launched its mainnet in October 2023 and serves as a data availability layer for various L2 rollups. Ethereum's roadmap incorporates a gradual, methodical implementation of DAS concepts, starting with architectural foundations and moving toward full implementation. EIP 4844, implemented in March 2024, introduces blobs, large data containers specifically for rollup data. This proposal reduces L2 costs by 100x, enabling more efficient data publication. Full danksharding, planned for future updates, will incorporate complete DAS sampling, dramatically increasing the security of rollups through DAS verification. This careful approach prioritizes security and stability while moving toward the scaling benefits that DAS enables. These challenges represent active areas of research and development in the blockchain space. Different implementations make different trade-offs in DAS implementation, which explains some of the architectural differences between Celestia's approach and Ethereum's planned implementation. Network latency and bandwidth are critical for efficient peer-to-peer data retrieval. Cryptographic overhead and data persistence are essential for ensuring data remains accessible for future use. These challenges are being addressed to advance the various challenges in blockchain scaling. Ethereum's danksharding uses KZG polynomial commitments instead of Merkle trees for more efficient proofs. This enables constant-sized proofs regardless of data size, requires a trusted setup ceremony, and allows for more efficient verification of availability. Proof of custody ensures validators must prove they've downloaded and stored data. Fraud and validity proofs optimize rollups use fraud proofs that require data availability. Distributed storage solutions, such as advanced storage systems like IPFS, Filecoin, ensure data remains available. These solutions address who stores the data long-term, ensuring that data remains available if verified. Data availability sampling represents a significant advancement in distributed systems theory. Byzantine fault tolerance offers a novel approach to Byzantine fault detection that requires significantly less communication complexity than traditional BFT protocols. Information theory provides a practical demonstration of using erasure coding and sampling to verify the existence of data without accessing all of it, a counterintuitive but mathematically sound approach. Probabilistic verification extends the field of probabilistic verification techniques, showing how statistical guarantees can be leveraged for practical security in distributed systems. Resource-constrained consensus enables participation in consensus by devices with limited resources, expanding the applicability of distributed systems to more constrained environments. These research directions show that while DAS has already enabled significant advances in blockchain scaling, there remains substantial room for further optimization and enhancement. The field is actively evolving, with both academic researchers and industry practitioners contributing to its development. As these advances are implemented, we can expect even more efficient and secure data availability verification, further extending the scaling potential of blockchain systems. Data availability sampling represents one of the most significant breakthroughs in blockchain scaling since the original Bitcoin paper. By solving the data availability problem in a novel way, it enables blockchain systems to scale to global demand while preserving the accessibility of these systems for their users. Understanding DAS is essential for anyone seeking to comprehend how blockchain technology can keep up with the Internet's demand to serve billions of users. For those interested in diving deeper into the technical details of DAS, there are numerous resources available. Academic papers, community resources, and technical documentation provide insights into the latest research and optimizations being published. The field is rapidly evolving, with new research and optimizations being published regularly. These resources offer a wealth of information for developers and researchers interested in exploring the potential of DAS further.